Hi all. In this video, we're going to look at the integral test of series. We're going to see how this test can be used to see if a series converges or diverges. We'll look at these three examples. We'll see if the test can be applied to them, and where it can, we'll move on to see how it can be applied to discuss whether a series converges or diverges. The first thing that we need to do is understand what determines convergency when you're using the integral test. Now here, we first define a function, a series, an, changing from n is equals to k to n is equals to infinity. Now, based on the structure of an, we define a function f of x. So the function f of x is the one that we're going to be integrating. Now, this function f of x has to be continuous on the interval n is equals to k all the way up to positive infinity. Now, for you to determine f of x, you basically get the structure of an, and in the structure of an, wherever there is n, replace that with x. So this is how we obtain the expression for f of x. And then next, there are three things that you need to check in terms of the nature of f of x. First, is it continuous? Secondly, is it positive? And thirdly, is it a decreasing function on the interval from k all the way going up to positive infinity with k included? If it does satisfy those three conditions, then you can move on to evaluate the integral. When you integrate f of x from k to infinity, if the integral converges, then so does the series also converge. Now, this expression can also be used to understand divergency. If the integral diverges, then we conclude that so does the series also diverge. So that is if it diverges. You might be wondering, uh, how does an integral converge? How does an integral diverge? Well, for an integral from k to infinity of f of x dx, we say the integral diverges. Let's say it converges. We say the integral converges if it reduces to just a real number k. Here, k has to be a finite number. If the integral reduces to that, then our conclusion is that the function f of x converges. If the integral, however, leads you into something like infinity here, meaning something which is not finite, then the conclusion is that it diverges. So here you have one that diverges, and then here you have one that converges. So this is how we determine whether an integral converges or diverges. Then I did mention to say that there are three conditions that you must check before using the integral test. Is it a continuous function? This basically means that in the interval k to infinity with k included, is it defined at all points? Meaning we shouldn't have a situation where for when x takes such a value in this interval, the function will not be defined, like a 0 in the denominator or a negative under the root. Do we have such numbers within this range that lead us towards that? If such numbers exist, then it won't be defined at those numbers, so it hence not continuous on the interval. If they do not exist, then we can conclude that the function is continuous. Next, we said it has to be a positive. It has to be positive throughout that interval. Okay, that's clear. Next, it has to be a decreasing function. Now, in some cases, you might find that it might be increasing at the beginning, but then eventually becomes a decreasing function. That will be okay as well. But generally, as you move on towards infinity, it has to show a decreasing property, not an increasing property, decreasing. Okay, so with those statements out of the way, let's see how to deploy the integral test. We begin with question 1 here. Can we use the integral test to answer whether that question converges or diverges? So let's look at this expression. Here, first we define f of x based on what an is. An is basically n ln n. So you have f of x is equals to, where there's n, we'll put x, and then lean x there. Now, regardless of, we know to say the graph of a lean would look like this. So the graph of a lean would look like this. And it crosses the x-axis when x is equals to 1. So this is the graph of a lean function. Now, clearly, from 2 to infinity, we see clearly that this function will always be positive. The values of x themselves are starting from 2 going to infinity, so those are all going to be positive values. Here we see that had the values of x be allowed to take numbers less than 1, for values of x less than 1 but greater than 0, you'd have seen that the function would have ended up being negative. The lean part would have been negative. So luckily, we are not including values less than 1. We're only going from 2 going up to infinity. So 2 would be maybe somewhere here. So from here going to the right, clearly we see that our function will all be positive values. The other thing that we see here is that had the range started from 1, then this would have been not continuous, because here, okay, yeah, this would have been continuous. That would have not been a problem. This would have been continuous as well for this version of a function. Okay, so this would have been fine too. But we see that, yes, it is continuous. It checks the first condition, continuity, on the interval. Next, yes, it's a positive. It's always positive, as we have seen on the interval. So the first two conditions for applying the integral test have been checked out. Now we check out the third one. Is it a decreasing function? Clearly, as we move from n is equals to, from x is equals to 2 going towards infinity, you can see that the values of the function keep on getting bigger and bigger. Because of that, this one turns out to be an increasing function. So remember, we needed it to be a decreasing function for us to apply the integral test, but because it has failed the third condition, we cannot use the integral test to check the convergency of this function. So that is an increasing function. So if you cannot use the integral test, you might want to check out the other methods to see if they can work. So here, since we are restricting ourselves to integral test, let's move on to the second one. Let's see if the test can be applied. If it can, how are we going to apply it? So when it comes to the second problem, we see that it's basically similar to the previous one, except we have that 1 over thing. So first we define our f of x based on an. This will be 1 over x ln x. So here, as you saw, this is always positive, so it checks the positive condition. Next, from n is equals to 2, from x is equals to 2 to infinity, we said this is always continuous. Now, this is where I wanted to say that if this had started from 1 to infinity, notice that ln 1 would have been 0. It would have been, at the starting point, it would have been 1 over 0, and this would have been undefined. So the second condition, the first condition for continuity, would have failed at x is equals to 1, which would have been included there. But luckily for us, we can see that our range there, our domain, is starting from x is equals to 2. So we're not including that 1 which have given us uncontinuity there. So if we're starting from 2, this will always be continuous, so that condition checks out. Is it a decreasing function? Well, in the previous example, we saw that this will always be increasing. Since this is into 1, if the denominator gets bigger and bigger, then overall the function will be getting smaller and smaller. Hence, we conclude that this is a decreasing function. So since the requirements have been checked, we can now deploy the integral test. So we now want to get the integral of our function x ln x from 2 to infinity. What will this integral be equal to? Because we know to say, using the integral test, after these conditions have been met, if this integral converges, then so does our series. So to integrate this, we're going to use a substitution we're going to let u be equals to ln x. When you get the derivative of u, we're going to get 1 over x dx, or we'll have dx is equals to x du. When we make our substitution, we're going to have the integral, and then this is going to be 1 over x. U, remember, where there's ln x, I'm putting u now. Where there's dx, I'm putting x du. The x and the x will cancel out, leaving me with the integral of 1 over u du. When I integrate this, I get ln u. So I get ln u there. I bring back what u is, so I get ln of ln x. So this is what I'm getting. And then the limits here. So of course, I'm ending with ln of ln u because u, as we said earlier, was ln x. So the limits I'm changing from 2 to infinity. I don't really want my x to ever be infinity, so sometimes here you see them using a limit saying that we are approaching infinity. When I get my my upper limit, I'll have ln of ln infinity minus ln of ln 2. Here what you see is that ln of infinity, since ln is a growing function, so ln of a bigger number will just be infinity as well. So we see that this part will obviously be infinity. So regardless of what ln of ln 2 is, if we are subtracting it from infinity, the answer will always be infinity. What are we saying here? The integral of 1 over x ln x has reduced to infinity. So this integral diverges. So the integral here diverges. So since this integral diverges, hence, even our series of 1 over n ln n also diverges. So remember, if the integral diverges, the series diverges. If the integral converges, the series also converges. Now let's check out the third example, and let's see how this one would work. For this one, we check continuity from n is equals to 0 to infinity. It will always be continuous. This one would want to give us any problems. Then we check, is it always positive? Well, regardless of the value of x you pick, this will always be positive. Now there's a problem on decreasing. Is it decreasing? Is it increasing? So this one is not really clear. So when we define our f of x based on our an, we're going to have x e to the minus x squared. So to understand whether this decreases or increases, let's try to use some calculus. So get the integral, the derivative I mean, to see if it has a turning point. If it has a turning point, we'll see the behavior of the function before and after that turning point. When we differentiate this to get f prime, we'll use product rule here. First, we'll keep e of x and differentiate x, which will be 1. Next, we'll keep x, differentiate e of x. In this case, differentiate the minus x squared, which will give us minus 2x. And then, of course, this will remain the same, e to the minus x squared. So by product rule, we'll get that. We can factor out the e to the minus x squared. Here we'll have 1. Here we'll have minus 2x squared. So to see the turning point of this function, we'll equate the derivative to 0. Since the exponent cannot be 0, it follows that then this other part must be the one which is 0 if the product is going to give us 0. So at 2x squared is equals to 1. X squared is 1 over 2, implying that x has two values. That would give a turning point. The function has a turning point when x is equals to negative 1 over 2, negative root of 1 over 2. It also has a turning point when x is equals to positive root of 1 over 2. Now, for our problem, the values of x are restricted to the range 0 to infinity. So since we are only focusing on 0 to infinity, we'll ignore the value of x which has a negative value, or the negative one, because it's not in our range. Our concern is only at x is equals to, I'll write this as 1 over root 2. So at that point, we want to know the behavior of the function. If this is the xy coordinate system, how is the behavior of the function? If this is at 1 over root 2, how is the behavior of the function from 0 to this point? And how is the behavior of the function from here going onwards like that? Is it increasing? Is it decreasing? So here you can use some test values. So we can get the original function, which is this, and get some test values there. So firstly, when you have f of 0, so since we're starting from 0 to infinity, for the first part I'm going from 0 to 1 over root 2, I want to see if it's becoming bigger or smaller. F of 0 will end up being 0. Now let's pick a number from 1 to that. Any number really will work. But what you'll see is that this function is x over e to the x squared. So we give us 0 when x was 0. But if x is non-zero, any number really, notice that your answer will be greater than 0. So if you pick a number a, for example, and this number is greater than 0, but less than 1 over root 2, notice that your answer will be non-zero and it will be non-negative. So your answer will be greater than 0. What does that prove? It actually proves that in the range from 0 to 1 over root 2, in this range, the function is increasing. You can actually use a calculator, pick any number that is less than 1 over root 2, but greater than 0, and substitute here. You'll see that the answer you'll get will be greater than 0, showing that the function is increasing. Next, we come to 1 over root 2. Since this is a turning point, we expect a change in behavior there. What will be happening going forward? Again, you can pick test numbers. Here, picking a number, let's say 2 or 3 or 4, anything really, but the number should just be greater than 1 over root 2. If you pick such a number and substitute in the function, notice that now, since you have x squared, not x squared, x over e to the x squared. In this case, when x is, let's say, 2, you're going to have 2 over e to the 4. 2 squared will be 4. When x is, let's say, 3, you're going to have 3 over e to the 9. What you'll see here is that the denominator becoming bigger faster than the numerator, implying that these numbers will be reducing. So from here going forward, we see that the function is actually decreasing. So this proves that eventually our function will be a decreasing function. Of course, it was increasing in the first small part there from 0 to 1 over root 2. But eventually, as we approach infinity, our function is a decreasing function. And that's all we need. We're not really, it doesn't have to be decreasing throughout the range, but eventually, as we approach infinity, it must be a decreasing function. So based on that, we can actually deploy the integral test on this function. So how is the test going to now come out? So of course, we're going to get the integral from 0 to infinity of x e to the minus x squared dx. To integrate this, we'll let u be equals to negative x squared, then du will be equals to negative 2x dx, and then dx will be equals to negative du over 2x. When we substitute, we now have the integral of this from this of x e to the u, where there's dx, we'll put minus du over 2x. This x and this x will cancel. The negative half will come outside, so that now I'll leave out the limits since I've changed the signs, the variable. So this is now just e to the u du. The integral of e to the u with respect to u will still be the same function. So I'll have minus 1 over 2 e to the u. I bring back my expression, my u. We said u was negative x squared. So you have e to the negative x squared. This, now we bring our limits. When we bring in our limits, first let's substitute the upper limit, e to the minus infinity, that will still be e to the minus infinity. Then minus the lower limit to be e to the 0. Notice that this is the same as, when you look at this one, it's the same as 1 over e to the infinity. E to the 0 will just be 1. Now, since e to the infinity is also infinity, so infinity into 1 will make this term to be 0. The negative, sorry, I put an e here, this is a 2. The negative and the negative here will give us positive. So that will just be positive half. So we have seen that our integral has reduced to half, and half implies that this one converges. So since the integral from 0 to infinity of x e to the minus x squared is equals to 1 over 2, which converges, then even our series from 0 to infinity of n e to the minus n squared also converges. Okay, so this is how we use the integral test to discuss the convergency or divergency of series. Okay, hope you found this video helpful. If you did, leave a like, let me know in the comment section. If you have any questions that you want me to look at, don't hesitate to reach out. You can, of course, always reach out on WhatsApp using that number. We have online math classes in case you want to join. You can also reach out for those if interested. Now, guys, we'll see you in the next video.